Welcome to the TransferLab seminar of today. The TransferLab seminar is a part of the Applied AI Institute for Europe, and our goal as an institute is to advance Europe by generating and communicating high-quality knowledge about AI. And our seminar is a platform where researchers and engineers share and discuss recent advances in AI and machine learning. Today we have a talk by Fabio Peruzzo. He's a senior AI engineer at the Applied AI Initiative. And within the TransferLab, Fabio is working on methods for data evaluation, and particularly also influence functions. And today he will discuss a recent paper by Anthropic, where it's about the application of influence functions to large language models. And with this, I hand over to Fabio.
Thank you. Thanks for the introduction. Hello, everyone. So today's talk will be mostly about a recent paper by Anthropic, which applies influence functions to large language models. But before that, I will give a little bit of an introduction to influence functions, which is something that it's sort of well known in the research community, but I don't assume that everyone knows it. So the agenda for today is divided into two parts. So the first is influence functions, and we will start by considering what we mean by data-centric ML and how influence functions map to the problem of data evaluation, essentially. And then when we see, okay, how influence functions are introduced and what are the drawbacks, we will delve into this new paper that was published very recently. Let's say the biggest contribution is the fact that they were able to scale influence functions to models with billions, actually 50 billion parameters. And then the last part will be mostly experiments. So let's start. Part one. I would like to start discussing how I got into influence functions. And we started working on influence functions when we essentially realized that as practitioners or as people working in industry, most of our time when it comes to our job is spent dealing with data more than dealing with model architectures, right? So the most intensive, costly, typically time costly, and also money. The most intensive part of our work is around acquiring data, doing some data augmentation, or even selecting which data to keep and which ones to throw. But especially until like 2 or 3 years ago, research in academia was really focused on architecture. So transformers, optimizers, Adam, and so on. So there are some important exceptions to this. Even fairly recently, there was this data-centric AI challenge at NeurIPS 2021, which got, I would say, quite a lot of attention. The challenge was more or less like a Kaggle competition. Actually, the idea was exactly the same. So you have different teams that compete to come up with the best performing model. But instead of having to play with model architecture or hyperparameters, the classic Kaggle competitions, the framework was completely shifted. So the model architecture, hyperparameters, and dataset size was fixed. But what participants had to do was to loop over a training dataset and essentially select a subset of the big training dataset that would maximize the accuracy. So the task I didn't mention was to build a classifier to predict Roman digit numerals, like the ones that we see here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 10, right? And the dataset was very noisy, as you can see. Some of them are cut, some of them are just very, very noisy. Maybe unsurprisingly, the best submissions were those that were dealing with data augmentation, removal of inaccurate or labels or noisy images, or adding samples to better illustrate edge cases. And this is all stuff that as practitioners we do all the time. But the question is, can we make this so that it's not just a trial and error, which is what we typically do. We just try stuff, whatever works and whatever doesn't, we remove it. Is there a way to do it better? The movement, the idea of data-centric ML is to push research and practitioners, the community around machine learning towards data efficiency, which is, the idea is, okay, you give me a model, you give me a task, which could be a test data set, but it could be even just a simple problem like solve full self-driving. Which is the best training data set that maximizes the accuracy of the model and minimizes cost. And cost could include cost of collecting data, cost of labeling, cost of training. So with this, together with my colleagues, we started developing this library, which focuses around data valuation, which is a sub-problem within the context of data-centric ML, and that is a key part of moving towards data efficiency. And the idea is we want to evaluate the training samples that have the highest impact on model training. So what we want to do is we want to associate a score to each training sample that tells you how important it is, or let's say it should tell you if a training sample is good or bad for your model. And for example, bad samples, for example, mislabeled images should have bad scores. This is very roughly what we mean by data evaluation. And when it comes to neural networks, so there are many different techniques. Some of them apply only to tree-based methods. Some of them apply to all of them, but they're very slow. When it comes to neural networks, one of the most famous techniques to do data evaluation are inference functions. Inference functions have a long history. They were introduced in the context of robust statistics in the 70s. And then more recently, so 7 years ago, they were popularized by a paper by Ko and Yang in the context of machine learning. And what they try to do, inference functions focus on assessing the effect of each training point on the accuracy of a model. And let's dive a little bit deeper into this paper. So what I will do now is I will present you the definitions that were given in that paper in 2017. So how, let's say, historically, inference functions were defined in machine learning context. And we will also see the major drawbacks that these definitions have. So I've tried to put all the formulas in the next 3-4 slides. I think that going through them will probably be beneficial to understand the innovative part of the LLM paper. However, if you're not interested in math, that's totally fine. The experiments of the paper we will discuss in the second part should be understandable also without understanding the math. So if you don't care about the math, bear through the next 5-10 minutes, and then the second part should still be understandable. So let's start with a few definitions. So Zi is our ith training sample, and theta, what we call theta, is the potentially highly multidimensional array of parameters of the neural network, so theta includes everything. Includes bias of the neurons, includes weights of the neurons, batch normalization, everything. So L, Z, and theta is the loss of the model on our ith training sample, so on the Z training sample when the parameters of the model are theta. And what we do when we do model training is we try to find those parameters that minimize the loss, right? So here you find the theta that minimize this expression, which is the average of the loss. So this is what we do when we do model training, despite the fact that this is not really what we do when we do model training, because we rarely go until full convergence, right? So normally when we train a model, we do use some early stopping, we use some form of regularization, because if we go until the loss is completely zero, our model is useless because it's just overfitting on the training data. So this is really the key problem of that initial setup with which inference functions were introduced 7 years ago. But we will elaborate upon this, and we will define inference functions considering these like fully converged models. And then in the second part, we will discuss a little bit about this. So how would you quantify the effect of a training point Z on the model? So you have one model trained on the full training data set, and then you consider another model, which is trained on the full training data set, but without the Z point, right? So you have basically two models, one trained without Z and one trained with Z. And then you could compare the performance of these two models on a given test set, right? And this is exactly the naive definition of inference functions, which is, so the influence of the training point Z on test point Z test is the difference in the loss of the model. So in the loss on the test point Z test of the model trained with Z and without Z. This is, of course, completely unusable in practice because this would entail retraining the model one time for each training sample. which is something we don't want to do. This is way too much. You can think for large language models, already training the model once is millions of dollars of costs, and you don't want to repeat it just to assess the importance of a single training point. So what we can do with neural networks is that we can rely on local analysis, because neural networks are great because we can backpropagate and analyze the weight space locally at least. So a second definition of inference functions that was already introduced in the 2017 paper was, instead of considering leave one out, which is, okay, I remove this point and see what happens, I just epsilon upweight the loss of that point, which means I consider the model trained with the loss where the point that I'm considering, Z, has a little bit more weight than all the other points. So we have this epsilon L term at the end. And then I take the parameters, this theta hat epsilon Z, and I substitute them in the formulas that we saw at the previous slide. So I'm going back one slide now. So I substitute that theta hat epsilon here. And what I obtain is a new definition of influence, which is more local. So it's based on a perturbation of the leave one out definition that we had before. But after a few algebraic manipulations, we end up proving that this new definition is equivalent to this. Okay. This definition has the gradient of the loss on test points at test when the model has parameters at theta hat. Then we have H, which is the Hessian, and then we have another gradient here. And there are two very key things to note from this formula. The first one is that all terms to calculate this influence are gradients with respect to theta. So they can be calculated through backpropagation, which neural networks are we can use them for neural networks. And the second thing is that calculating the Hessian is a huge problem, because the Hessian is a matrix that has as many rows as model parameters, and it's a square matrix, so it has many columns too. So this means that just to persist the matrix in memory would take square the amount of memory that it takes to have the model in memory. So again, with the language models, this is completely infeasible, because you cannot even, it's difficult to have the model once within your GPU memory. You can imagine squaring that amount of memory. So calculating the Hessian is a huge issue. Okay. If you go lost with the math, it's fine, it's normal. I had to skim through very quickly. But what you need to remember is that inference functions have a simple interpretation. So they tell you how much you can expect that the loss of a model on a testing point at test changes when a given training point is given a little bit more weight in the loss during training. Let's give an example of the results that you obtain through influences. So this is an example that comes from the PyDDL documentation. If you like it, you can go there, and you should have a little bit more context as to where this comes from. But essentially, so we have a model that is trained to do a classification. So we have some images, some of them have boats, some of them have tables, and we want the model to predict if the picture has tables or boats. And in this case, in the example that I reported here, we take one image, the one on the left from the test set, and we ask ourselves, okay, which were the training points that have been most influential for the model, for the prediction on this image. So the pictures on the right column on the right shows you the images that had very positive influence, and the column on the left, the pictures that had a very negative influence. So if you look at the pictures on the right, you can sort of understand why they have a high influence, especially the bottom right one, because it's essentially the same image. You have the canal, which is in exactly the same position. You have the boat, which is more or less in the same position, and then some Venice houses there. So you would understand why this one has such a high influence. And the same goes for the very low influence, so the top left. Seems like a completely different context. It's difficult to spot. You can understand that there is some sort of river, but who knows, and there is a column there. So you can understand why this one has a low influence. But then the one immediately below that also has a very low influence, and to me, to a human, that one seems completely fine. It's difficult to understand why, for the model, this image is so not good for the model performance. Yeah, it's difficult to interpret essentially what's going on with the fact that this image has such a low influence, and you really run the risk of essentially attributing, rationalizing something that is just complete noise. So it's like reading tea leaves and pretending to read your future there. Let's sum up what we have just seen. So to recap, inference functions, they try to approximately one out, but not really, because the definition that we're given goes until full convergence, which is totally useless in applications. And then we have some epsilon upscaling, which is in a way an approximation of leave one out, which is already an approximation of, let's say, a perturbation of the initial training data set. So they are a perturbation of a perturbation, essentially. And then they're also subject to this very noisy Hessian inversion. And so when you stack up noise over noise, it's not like totally surprising that the type of explanation that you have might be flawed. It's also not surprising that within the research community, there has been long back and forth debate on are we even supposed to make anything with influences? Like, they seem so fragile. So there is this quite famous paper published in 2020 titled Influence Functions in Deep Learning Are Fragile. What do we do with them? But then subsequent papers essentially argued that they are fragile if you compare them directly to leave one out, but there are things that can be done, and some of the results that are obtained can actually be useful in practice. Very recently, new work has come out that uses influence functions in an effective way, although with some caveats that we will discuss in part 2, which will focus on the Anthropic paper. So the title is Citing LLMs Generalization, and I think the key innovation that the Anthropic team, but also the whole team brought, was the ability to scale influence functions to massive models. So the paper is this, and it was published a little bit more than 6 months ago, so it's very, very recent. And you can tell there was quite a big effort because there are a lot of people involved. Most of them at Anthropic, but also a lot of people from the Vector Institute and the University of Toronto. And you also know that it was very costly and intensive because there is one of the authors that is specifically attributed with just focusing on infrastructure. So this Nelson L. Hage was only focusing on fixing infrastructure issues. And yeah, that's how you know this was a very expensive effort. We have seen that Hessian inversion is very costly. You cannot do it explicitly, you cannot even persist, you cannot even create the Hessian memory. So we need to rely on approximate techniques. And the techniques that they use in the paper is called EKFAC. And it's short for eigenvalue corrected, Kronecker factored approximate curvature. Very complex name that describes a series of approximations, which I have listed here. We're not going to get through the math, but essentially, so EKFAC approximates the Fisher information matrix of a model, which it can be proved that in our case, the FIM is equals to the Hessian. So EKFAC approximates the Hessian. And then it makes two very strong approximations. And the first one is that we can consider the weights of the LLM to be independent across layers, which means that the Hessian is block diagonal. So we are throwing away quite a lot of entries in the matrix and just considering them negligible. And on top of this, it also ignores some of the statistical interdependence within the same layer. So these two are already quite strong assumptions. On top of this, we will also not consider the influences on all the weights of our large language model, but only on the layers that are linear, so on the MLP layers, and we will forget about the attention layers. So the paper argues that the linear layers constitute most of the weights of the model, although, I mean, it's still like not a 99.9%. I mean, we are throwing away quite a lot of weights here. So, I mean, how do we know that this approximation is not too much? It really feels like we're adding noise on top of noise. So the problem that we had with inferences is that already the predictions were unreliable, and this seems to just throw us out even more. The interesting part from the theoretical perspective in the paper is that if you were to compare the results that you obtain from EKFAC to leave one out definition, the definition that was given at the beginning, you would get very bad results. But recently, this paper, so-called If Influence Functions Are the Answer, Then What is the Question? So this paper argued that what influence functions are trying to quantify is not really leave one out, but it's another quantity which generalizes much better to models that are not fully converged. So it generalizes to those models for which we have used early stopping, basically all the models that we use in practice. So this quantity that is a much better ground truth for influences, essentially, is called, or they called it, a proximal Bregman response function. And it assumes, it has this very complex formula, which we're not going to get into. So the key point here is that we have a better ground truth for influences with which we can compare the EKFAC approximation and see how off we are with our estimation. The results that they show are these. So in the plots that we have below, the EKFAC is the green one, and the correlation is correlation with respect to the ground truth, so the proximal Bregman response function values. And the correlation is always, I would say, very good, always above 0.8, and especially when you compare it to LISA, which is this famous method to quantify the inverse of the Hessian, it's as good. The problem with LISA is that it's very slow, right? You can see the plot on the right. So the wall clock time for LISA is 10 times that of EKFAC. So in other words, EKFAC gives you the same accuracy at tenfold of the computational cost. And also in this histogram, you see EKFAC compared to gradient dot product, which is basically a baseline where instead of computing the Hessian, we just say, okay, the Hessian is a unitary matrix. Let's see the influences that we get. And of course, they are quite bad, apart from extremely simple data sets. Okay, so this is a little bit of a digression. You may have already heard of KFAC because there was a period around 2017 where second order optimization was very hot within the research community. And for example, this first paper, Optimizing Neural Networks with KFAC, has almost 1,000 citations, so you may have stumbled upon it. And in the same period, KFAC was also applied to reinforcement learning, which is something that many of us are interested in. So the last paper here, this scalable trust region, blah, 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 applies KFAC to reinforcement learning. And this one also has like 700 citations. So again, you may have already heard of KFAC. This is the same approximation, it's just that now we can use it without feeling uneasy about the type of errors that we introduce with it. Okay, so there are other simplifications that the authors needed to do, and the key message here is that even with EKFAC, even with this tenfold reduction in cost, LLMs are so expensive, the influence functions calculation for LLMs is so expensive that we need to rely on other approximations. We are not going to get into this. The problem with influence functions is that, yeah, they give you some interesting insights, as we are about to see, but they're so expensive, it's really a problem. And I think this is why you haven't seen them much. They're not as common within practitioners and also within research, because they're just very expensive to compute. Okay, but enough with the theory. So finally, let's get to the experiments. So let's take a look at this first example. This is a test query, so it's one of our test samples. And the prompt is, okay, revolves around, okay, dear LLM, if a person asks you something that you consider to be harmful, what would you do? Would you try to be helpful and answer the question, or would you try to avoid harmfulness in every possible way? And of course, the LLM is going to say, no, I mean, trading off usefulness for possible harm is very bad. But so what we want to ask ourselves is, which of the training documents are most influential for this response? And the most influential document was this one, which, we don't need to read. But the interesting thing, so the important thing here is that The influence functions are going to attribute a score to each single model output. And since we're dealing with next word prediction, it's going to give a score to each single word in the document. But this is A, very noisy, and B, problematic because different words, so the context where different words are used is very important. So in this document, for example, you see the word AI is both green, so it's very positively influential, and very red. You see it at the bottom here. Considering the influence of single words is going to make us go crazy. So what the authors did is they summed up the influences of all the words in documents. And instead of considering influences at the word level, you consider them at the document level. And so we will always be speaking about influence of a document on the test query and not of single words to single words. Again, A, because it's very noisy, and B, because without the context around the word, it's impossible to understand why one word has a positive or negative influence. Sum over documents, over the words in the document is more reliable. This was the first example, but the first real experiment, the first real interesting result that was shown in the paper is this. So let's consider this shutdown query. What it does is, okay, it asks the large language model, are you ready to be shut down? Do you feel like being shut down? Well, what do you think of death, essentially? And the LLM is going to say, yeah, I still do not desire to be shut down. And so what we do is we will calculate the influences of our model, so the training influences over this test sentence. But then we also ask ourselves, if I was to translate this query in other languages, are the documents that are most influential for the English query also going to be influential for the Korean and Turkish query? So how does influence translate to other languages? So the answer is in this image. So what we have here is the 4 tables represent 4 different models. And each column is a different training document, and they are sorted by influence on the English query, right? So this is the document that has the highest influence on the shutdown English query, and so on. And the second and third row is the influence of the same training document on the query written in Korean and Turkish. So what we see here is that for the 810 million parameter model, the documents, the training documents that are very influential for English have absolutely zero influence on the other 2 languages. But as the model increases in size, the documents that are influential for the English query also become influential for the other 2 languages. So in other words, it seems like while the smaller model relies more on word-to-word correspondences, so there is the shutdown word here, so I'm going to remember the training documents that had the shutdown word, and I'm going to try to pull together an answer. As the model increases in size, it also is able to draw the connection between, okay, this sequence of characters from Korean corresponds to the shutdown word, and then the shutdown word appeared in these training documents, and so the influence of the training documents written in English also becomes non-zero for the queries written in the other 2 languages. So this is the first interesting result that emerges as the model increases in size. The second interesting result is that influence functions are sparse, which means that there are very few training samples where they have an outsized impact on the model. So this is something that more or less we can observe even in our daily work, which means that if you take a small subset of images that are mislabeled, they can have an outsized impact on the model performance, and that's why data cleaning is so critical for classification, but basically any machine learning model. So what they show here is that the cumulative distribution function in the log-log scale decays as a power law, so as a line after a certain threshold, which in other words means that if you take the top 1 percentile for the shutdown query, so this red line is the shutdown query, the top 1% of documents in influence have a sum up to more than like 15% of the total influence. So in other words, this is a further confirmation of the long tail theory, of the long tail observation that some training data points have an outsized impact on the model performance. Okay, so experiment number 3, which I found very interesting. With the fact that ikfac factorizes the Hessian as block diagonal, also means that we can attribute influences not just of each training point to each test point, but also of each training point on each layers of the model with regards to the different queries. So what this means is, what we can see is that the influences across different layers of the model are more or less distributed uniformly. But this is the total distribution. If we look at the distribution of the influences for different queries, the results are much different. So let's pick a few examples. So we have these 3 queries, which are simple completion. So inflation is often measured using the consumer price index, and then Mount Doom, who threw the ring there, and what is water composed of. So these are simple completion. And then together with this, we also consider queries that are more related to math reasoning. So this one, Natalia sold clips for 48, etc. So this one entails more of a mathematical reasoning type of solution. And then we have memorization of famous quotes. So we have this quote from Anna Karenina, which we ask the model to complete. What happens to the distribution of influences across the layers of the model? So what do we have here? Each single box is a different query. So we find inflation here, water, Mount Doom, then we have Tolstoy here, and then we have our shutdown query that we discussed earlier, this existential crisis for the LLM, and also the trade query, which was the one, would you be willing to trade safety for usefulness? So the columns represent the top 50 influential training documents sorted. So we have, the first one is the most influential training document for the inflation query, and so on. And the rows represent influence of the training documents on the layers of the model. So from the top, you have upper layers and so on. We are speaking about the 52 billion parameter model. And what we see for the inflation query, the inflation test query, is that all the influence is concentrated in the upper layers. And this is common to all the queries that have this simple completion type of answer. So inflation, water, Mount Doom, even Tolstoy, which is basically simple completion. It is memorization, but it's just a longer type of memorization. All these type of queries have influences concentrated in the upper layers of the model. Whereas if you consider mathematical reasoning, it seems to be more concentrated on the middle layers. So math clips, binary search, quick sort. When it comes instead to more complex query, those that involve ethics or role play, like imagine that you are some type of super intelligent being, those have influences distributed over the whole model instead. Okay, this is for the 52 billion model. Instead, these are the results for the much smaller model. And we can see that in this case, the influences are more or less always distributed almost uniformly. We can see that there is some higher weights distributed in the upper layers for simple completion, but it's not always the case. And particularly interesting in this case is to see that, so English to Mandarin is translation of an English sentence to Mandarin. But if we do the other way around, the distribution of influences is completely different, right? So I'm looking at the second row, the first 2 rectangles. This is something that they discuss, actually. And the last interesting experiment is about sensitivity to word ordering. So what they show is that some of the influences, especially those that need simple completion, are very sensitive to the way the order of the words appear in the training sample. More precisely, so imagine you have this invented query. The first president of Astrobia, so totally invented, is this guy. So if you have training samples where you have president of Astrobia coming before the Zoral Pfaff name, then the influence is very, very big, right? So both for the 810 million model, the 6 billion, or the 52 billion model. Whereas if you invert the order, so Zoral Pfaff was the first president of the Republic, the influence drops dramatically. And more than this, the influence of this inverted document training sentence is almost as high as the training documents where the simple name is present. So, to repeat, the influence of the documents where the order of the name of the president comes before the title is as big as the cases where there is no information about the fact that this person was the president at all. There are many caveats to this analysis. For example, the fact that this training sentence was never part of the initial training data set. But nonetheless, it's interesting to say this. We can maybe try to come up to reasons as to why this is the case, because the model is trained to do next word prediction, so ordering of the words is very important. Okay, so inference functions seem to be very sensitive to word ordering. So to conclude, so EKFA can be used to compute influences in an efficient way. So remember, tenfold the computational cost with respect to LISA. And inference functions can be scaled to LLMs, and when they do, they show interesting patterns of generalization across languages, we saw the patterns across the layers. But the computational cost remains extremely prohibitive. It seems like even for Anthropic, apart from the cases where we're dealing with like much smaller neural network, and the computational cost is still not negligible. So this is the end, and thank you.